Hello everyone, I am Jian-Wei He from the Hong Kong Polytechnic University. Today my presentation is about the study of second-order effect of steel posts supporting Rockfall flexible barrier. This work is collaborated with my supervisor Professor Chen, Dr. Liu, and my colleague Dr. Zhao. Firstly, I would like to introduce the flexible barrier system. Foreign laws are commonly seen in some mountainous areas and they will cause severe damage to the residential buildings, highways, and railways. So flexible barrier systems are applied as a protection structure to intercept falling logs at the slopes. The system generally consists of steel posts, ring net, and steel cables and braid devices. We can regard it as a special type of steel structure. Comparing with the traditional ridge barriers such as embankment and rock sheds, it can be rapidly installed, easily maintained, and it is also environmentally friendly. This figure shows a flexible barrier installed in Hong Kong, and we can see that the flexible barrier requires less area to install, and as the components of the system are prefabricated in the factory, they can be easily assembled on site. Comparing with the rigid barrier, they cost less, and finally, they are unnoticeable in the environment. The system generally consists of steel posts, ring net, steel cables, and braid devices. The steel cables can support and connect the ring net to the post, and the ends of the cables are anchored in the ground. And braid devices are the energy absorber, and they can also provide elongation for steel cables that they are connected to. Steel posts will support the whole system and build the intersection surfaces. The ring net are intersection structure to stop the falling logs. These three figures shows the process of the system to stop the falling boulders. When the boulder contact the net, the ring net will deflect along with the boulder. At the same time, the boulder's velocity will be reduced. And finally, the boulder will be stopped, and the brake devices connected in the upslope cables will be elongated. And this elongation will absorb energies and provide us space for the system to deflect. From another view of the system, you can see the cables in magenta color. They will slide during the process to contribute to the deflection of the ring net, and this process will help to stop the boulder. And during the process, we can see the steel post will be under compression. As we have mentioned, the post will be in compression during the process. The failure mode of the post can be found from the site investigation that the buckling will occur. When the buckling occurs, it will reduce the height of the barrier. And when the posts continue to deform and the system cannot resist any subsequent impact, and the failure of the post might lead to the collapse of the system. And the failure of steel post can be also found from the full-scale test. This is a full-scale test of a flexible barrier with a rated energy of 1,500 kJ. The test is conducted subject to the requirement of ETAT 27. We can see the boulder is stopped by the system, but the buckling of edge ball is found. This is a figure shows the detail of the deformed edge post of the test. During the test, the post will suffer a tension force from the left side. And finally, the post head displays left forward for about 750 millimeter. The rupture is also found at the cable that connects to the post, and this test fails to meet the requirements specified by ETAT 27. And from the site investigation and this full-scale test, we can see that the capacity of steel posts should be carefully considered in this system. The current design of the system relies more on the flexible full-scale test, and no member capacity checking has been conducted during the design stage. And generally, the length of the post is more than 4 meters, and only the post head and toe are restrained by the cable ropes or base plate. And for such a slender post, there's no intermediate restraint. So we propose a simple model to analyze the edge post behavior when the system is subjected to boulder impact. And this model is simple and only includes the steel post and the cable ropes that are connected to this post. And then the second order effect, especially the member initial imperfection, will be considered. You can see this simple model. The configuration will reverse to the full-scale test, and the steel post is with a length of 5.5 meter, and a notional horizontal force of 100 kilonewton is applied at the post head. This is a force to represent the cable that connected to this post head, and to simulate the effect during the impact process. And the steel post member initial imperfection refers to Hong Kong code, and we can see that along the minor axis, the initial imperfection is 1/400 of the length, and along the major axis, 1/300 of the length is applied. And the section capacity of the steel post is checked by this equation, and it includes the effect of axial forces and bending moment. In the bending moment, the moment which induced by the initial impression were also included. This is a modeling result. We have two cases. In the first cases, the initial imperfection of the post is included in the analysis, and in the second one, the initial imperfection is not included. And when we have checking that if the phi reaches 1.0, when phi reaches 1.0, it means the buckling occurs. And in the first case, when the phi reaches 1.0, the horizontal force is about 167 kilonewton. In the second case, it will be 185 kilonewton. So from this simulation result, we can see the steel post buckles when the force is about 167 kilonewton, which is much lower than the minimum breaking force of the cable, which is 252 kilonewton in this case. And the cable force should be limited to a relatively low value to avoid the failure of the steel post. When the member initial imperfection is considered, the horizontal force causing the buckling of the steel post is about 11.4% lower than that without the consideration of member initial imperfection. So we can see it is a very significant effect on the buckling resistance of the post by member initial imperfection through this modeling. Here comes the summary of this presentation, and we can see that the buckling of steel posts is found in the flexible barrier system from the site investigation or the full-scale test, and it will cause the collapse of the system. So we propose a simple model to analyze the behavior of the edge post when the system is subjected to the boulder impact, we only consider the edge post and some cables connected to this post. And in the analysis, we apply the member initial imperfection to the post and find that if we consider the second order effect, the horizontal force that caused the buckle of the post will be much lower than that without the member initial imperfection. And so we can say the capacity of the system, the steel post and the system will be overestimated if we don't consider the member imperfection. So in this research, we will emphasize that the second order effect of the steel post in the flexible barrier system. Okay, that's my presentation. Thank you.